Hey again, everybody. Welcome back. We're going to continue from where we left off in our last lesson where we learned about polar coordinates. We were able to write numbers that were in rectangular coordinates or Cartesian into polar form. But now we're going to look at polar form of complex numbers. So we want to be able to say that we can write complex numbers in polar form and say that we understand the relationship between two complex numbers and their product in polar form. So first thing, task 1. We know that points in the Cartesian plane or rectangular plane can be written in polar form. And since we can represent complex numbers, which are in the form a plus bi, in the complex plane in a similar way to rectangular coordinates, that is, we can go horizontally and then vertically to get to any point in the complex plane, shouldn't we be able to do the same thing for complex numbers? So let's test it out. Let's consider an arbitrary, again, arbitrary meaning completely random complex number. We're going to call it x plus yi this time, where x and y are real numbers. It can be anything we want. That's why it's arbitrary. Let's graph this point on the complex plane to see if we can come up with a way to write it with a polar coordinate system in mind. So I'm just going to put this point really randomly. Let's call, I'll put it right here. This is our point. We'll call it x plus yi. And as we have, I'll draw a radial measure out to it. So we plotted it, and we're going to label that radial distance r and the angular distance theta. So similar to what we did with rectangular coordinates, we were able to do this with complex numbers. Remember, this is the imaginary axis. This time, not the y-axis, and this is the real axis. This point we just found up here was at yi in the imaginary direction and x in the real direction. So we want to be able to figure out now, how can the horizontal distance, that is in the real direction, be represented as a trigonometric function? We're going to try to get this in terms of our radial measure, r. Well, that horizontal distance is just this right here. It's x. Well, we can form a right triangle out of this as we have. I didn't draw that perfectly, but there's our vertical distance. This is just, we go up y units. Yeah, it's in the imaginary direction, but its length is y. That's the real number. So we have a right triangle again. And we can use our trig relationships. When we're looking at this value down here, if we think of theta, that horizontal length x is adjacent to theta. We want it in terms of r as well, so that's our hypotenuse. Our trig relationship there should be cosine, the adjacent divided by the hypotenuse. So we can set up our trig function. Cosine theta is equal to the adjacent side x over the hypotenuse, which is r. But we want to know how we can represent that horizontal distance. That's x. Let's solve for it. To solve for x, we need to get rid of the division of r, which means we'll have to multiply both sides of our equation by r. Times r on the right side, times r on the left side. On the right side, r divided by r is 1, so all that's left here is x, and then we'll have r cosine theta. Therefore, we have r cosine theta is equal to x. So now we have represented the horizontal length as a trig function. X is equal to r cosine theta. Now the same thing, or similar thing, it's asking, how can the vertical distance in the imaginary direction be represented as a trig function? So that's our length y right here. We know, if we look at our triangle, y is opposite of theta. We know r is the hypotenuse, so our trig ratio here should be for sine, because sine theta is equal to the opposite y over the hypotenuse r. Same thing, we need to solve for that vertical distance y. We'll take sine theta on the left side and y over r on the right side, and multiply both sides by r. Once we do that, I actually have space to write it here. I'll write it over here. We end up getting, let's cancel, r sine theta is equal to y. So now we have written the vertical distance as a trig ratio, or trig relationship. So this is r sine theta. So now we want to substitute both representations for x and y in the complex number x plus yi. So our complex number, color coordinate some things. We add x plus yi. Well, let's just substitute what we found. What we found for x was r cosine theta. We saw it up here as well, r cosine theta. So in place of x, we'll substitute that, r cosine theta. Plus, for y, we found r sine theta. So we'll substitute that for y. And then we still have this imaginary number I. So now we have it in this form using our r and our theta. So this is a polar form. We can simplify one thing real quick. Notice r is in both terms, therefore we can factor it. So let's factor r, I'll do that red, out of both terms. So we should end up with, r times cosine theta plus sine theta. And then I. Conventionally, this isn't the way we normally write it over here with the I after sine. So I'm just going to rewrite this real quick as r times cosine theta plus I sine theta. For some reason, somebody a long time ago decided, let's write the imaginary number I in front of the trig function, and it'll look nicer. Therefore, we have polar form of a complex number. Any complex number can be written, or we'll call it a plus bi, can be written in polar form. Which is a plus bi is equal to r cosine theta plus I sine theta. And this is where r is our radial distance. And theta is our angular distance. So with this in mind, let's take a look at an example. This with actual numbers instead of just variables. That was the general case. Let's look at it for a specific case. This time we're looking at the complex number z, which is -1 minus 2i. How can we write this complex number in polar form? Well, -1 minus 2i, -1 is maybe here. I didn't put a scale on here, which is fine. And -2i, this is -i, and let's make this -2i. We'll put our point z approximately right there. So follow this process we're starting to get used to. Let's draw our radial distance outward. That's r. And our angular distance, starting here, is theta. And we'll form a right triangle out of this. This is our vertical distance to that point, which we know is 2. Yeah, it's in the negative direction, but it's a length. So lengths can only be positive. That's why I'm writing it as positive 2, even though directionally it went down 2. And the horizontal distance is 1. Went left 1. And again, it's a positive just because it's a length. I'm ignoring the directional aspect right now. All right, so first thing, we need to figure out something about the angle. This angle in here is not theta. That again is our angle we're calling alpha. Notice that's a little more than 180 degrees. We'll get to that in a second. So first thing, we want to find alpha. That'll be our first step. Find alpha. Well, to find alpha, what we know about this triangle is the opposite side and the adjacent side. So the trig ratio that's useful here would be tangent. Tangent alpha is equal to 2 over 1. The opposite side was 2. The adjacent side is 1. To solve for alpha, we'll take the tangent inverse of both sides. We have tangent alpha here. 2 over 1. What I'm doing is taking the inverse tangent of both sides. To do that, we know that tangent inverse and tangent are inverses, so they undo each other. We end up with alpha is equal to tangent inverse of 2 over 1, or really just 2. So let's take a look at Desmos for this. Tangent inverse of 2. You could put the over 1 if you want. It's not going to make a difference. I'll put it just to be explicit. And we get 1.107. That's in radians. In degrees, we get 63.4. I'm going to use degrees right now. If you want to use radians, you're more than welcome to use radians. I'm choosing to use degrees. We get 63.4 degrees. So that's alpha, this angle, 63.4 degrees. But we want to know what theta is. As I mentioned, alpha is a little more than 180 degrees. We know halfway around is 180. So to find theta, we know that it would be 180 degrees plus alpha here. in order to get to theta. So our next step to find theta should be equal to 180 degrees plus alpha. We just found alpha. That was 63.4 degrees. So theta would be 180 degrees plus 63.4 degrees. Therefore, theta is 243.4 degrees. Put this on the graph, 243.4 degrees. That makes sense. It's more than 180. It's in quadrant 3. So we've now found theta. Other thing we need to know is, what is r? So our third step here will be to find r. This is the simple part. To find r, you know two sides of this right triangle. Therefore, we can just apply the Pythagorean theorem. R squared equals 1 squared, the horizontal length, plus 2 squared, vertical length. So r squared equals 1 plus 4. R squared is equal to 5. Take the square root of both sides, and you should end up with r equals the square root of 5. You can approximate that as a decimal, but square root of 5 is our exact answer. So I'll leave it like that. And now we know r, we know theta. We can write in this form we just discovered up here. R, theta, plug those in, and we would have our polar form. So, last step. We'll write z in polar form. Z will be equal to r, which is square root 5. I'll just write this form up here. It was r cosine theta plus I sine theta. So in our case, it's square root 5 cosine theta we found was 243.4. Plus I sine of 243.4. And there's our polar form for this number z. So I'm going to give you a chance to do a couple of these as examples. So in task 2, just to get used to this process, take a few minutes, pause this video, convert both of these numbers, u and v, to polar form. I recommend drawing it on the graph to give yourself a chance to actually visualize what this looks like and draw the angles. All right, now that you have taken a second to do this on your own, I did this earlier. You can now double check your answers for what you got here. Pause the video and you can take a look at these to follow step by step. U we found was square root 13 cosine 56.3 plus I sine 56.3. I also did in radians too if you chose to use radians. And V is 5 cosine 126.9 degrees plus I sine of 126.9 degrees. Right, so that's how we can convert any complex number to polar form. So now that we have that idea down, polar form is going to be helpful when we multiply complex numbers. It's going to give us a better perspective of what's happening geometrically when we multiply complex numbers. So in the past, we've seen how we can multiply complex numbers when they're in the form a plus bi. That's easy. We're going to do that right now. Let's find the product of the two complex numbers, u and v, from task 2 when multiplied by the complex number z from task 1. So in the first one, we're going to multiply that number z by u. Well, z, going back to the first page, is negative 1 minus 2i, and u is 2 plus 3i. So z is negative 1 minus 2i, and u is 2 plus 3i. Let me double check just to make sure that I said u correct. 2 plus 3i. And multiplying complex numbers in this form is basically the same thing as multiplying binomials. You can distribute, or I like to use a box to organize my thoughts. So I will draw the box here, not a circle. First number was negative 1 minus 2i. Next number is 2 plus 3i. Negative 1 times 2 gives me negative 2. Negative 2i times 2 gives me negative 4i. Negative 1 times 3i is negative 3i. And negative 2i times 3i, negative 6i squared. So we can write that out. Negative 2 minus 3i minus 4i minus 6i squared. And now just simplify. Negative 2, negative 3i minus 4i, negative 7i. Hey, we know what I squared is. Just a reminder. I squared equals negative 1. So let's substitute negative 1 for I squared. Further simplification, we have negative 2 minus 7i. Negative 6 times negative 1 is positive 6. Now we have these two like terms. Negative 2 plus 6 is positive 4 minus 7i. So now we know that z times u is 4 minus 7i. We'll be using that. So take a second, do this for z times v, pause the video, and then I'll share the answer with you. All right, now that you paused the video and done that on your own, what you should end up with here, when you multiply z times v, is 11 plus 2i. That's what we get when we multiply z times v. All right, so let's take these ideas and do something with it on the next page. What we're going to do is look for a relationship between the product of z and u when written in polar form. So first, let's graph all of those numbers together. Z was equal to negative 1 minus 2i. U is 2 plus 3i. And we just found z times u on the other side. Z times u was 4 minus 7i. So let's graph all of these together. Z is negative 1 minus 2i. U is 2 plus 3i. And z times u, we found found up here is 4 minus 7i. So 4 and then negative 7i. Graphically, it might be hard to see a relationship right here, just looking at it so far. So let's work with these. Next thing we need to do is convert the product of z times u, to polar form. So we're going to convert this number, 4 minus 7i, to polar form. This angle all the way around is theta. And this is our radial measure, r. Let's form a right triangle out of this. Let's do this in green real quick. All right, so this length is 4. This length is negative 7, or really it's just 7. And then this angle in here we'll need to know. That angle is alpha. So as we have to figure out what alpha is, we need to use tangent, because we know the opposite and the adjacent sides. So let's figure out alpha. Tangent alpha is equal to 7 over 4. Apply the inverse tangent of both sides. You should get alpha equals tangent inverse of 7 over 4. And with a calculator, tangent inverse of 7 over 4 gives us 60.3 degrees approximately. So alpha is approximately 60.3 degrees. All right, but we don't want to know alpha. We want to know what theta is. Theta is all the way around to this point right here. The full circle would be 360 degrees. So we need to take away alpha from 360 degrees to get theta. So theta should be 360 degrees minus alpha, which was 60.3 degrees. Therefore, 360 minus 60 is 300, minus 0.3 gives us 299.7 degrees. All right, so we know theta now. Cool. We just need to figure out r. Quick calculation for r. R squared equals, the length of this was now 4 squared plus 7 squared from our triangle down here. 4 squared, 16. 7 squared is 49. The sum of 16 and 49 is 65. Take the square root of both sides, and you have r equals the square root of 65. 65 is not a perfect square, and if I go through my perfect squares, I don't think any of them go into it. 4 does not go into 65. 9 doesn't. 16 doesn't. 25 doesn't. 36 doesn't. 49 doesn't, so on. So we'll just leave it as r equals square root 65. Now we can finally write our answer. This number, z times u, in polar form, is r, which is square root 65, times cosine theta, which is 299.7, plus I sine the 299.7 degrees. So now let's just list these out. That way we can start to examine some sort of a pattern that's going to happen. Going back to the first page, we found z in polar form. polar form, z was square root 5 cosine 243.4 times I sine 243.4. Square root 5 cosine 243.4 degrees plus I sine 243.4 degrees. All right, we also found u on the last page. So going back to the last page, u in polar form was square root 13 cosine 56.3 degrees plus I sine 56.3 degrees. Square root 13 cosine 56.3 degrees. Plus I sine of 56.3 degrees. And next, we found z times u, which we just wrote up there was square root 65 times cosine of 299.7 degrees plus I sine 299.7 degrees. All right, with this in mind, what I want you to do is just take a look at these three numbers, see if you can theorize what a relationship would be between the numbers z and u that we just found and their product. Is there a pattern? Is there something happening here? All right, what I'm noticing, if I were to multiply 5 and 13, notice they're both square rooted, that should give me square root 65. So it seems like this is coming from multiplying square root 5 times square root 13. And this 299.7, looking at the angles up here, 243.4 and 56.3, if I were to add those two numbers together, 243.4 plus 56.3, that gives me that 299.7. So this is really a quick way that we can actually multiply complex numbers. If we have them in polar form, seems like what's happening is we're multiplying that r value, the radial distance, to get the radial distance of the new complex number, the product, and then just adding the angular distances of both complex numbers. Let's test to make sure that this isn't just a fluke and that didn't happen for that one special case. So I want you to repeat the process for number 3 on your own. This time it shouldn't be z and u. It's a typo on my part. This should say z, v, copied and pasted too much. And again, this is v as well. All of those u's should be v. Hey, I did it there. Look at me. Okay. So pause the video, go ahead and do this on your own. All right, coming back from pausing the video, here is my solution for number 3. And let's test to see if that pattern that we noticed is happening again. Z had a radial distance of square root 5. V had radial distance of 5. Hey, this is just coming from multiplying square root 5 times 5. flipped it around, but multiplication's order doesn't matter. But right now, what happens when we add these two angular distances, 243.4 and 126.9? Plus 126.9 degrees. All right, if I took those and added them, 243.4 plus 126.9, I get 370.3. Is that what we wanted? Doesn't seem like it's that 10.3, but see a 0.3. What is this? Well, we know that 370.3 is really just 360 degrees plus 10.3 degrees. So when we calculated it, we got just that small angle. This is like us going around the circle, 360 degrees, plus theta was 10.3 degrees. We could also have thought of theta as around the circle once, just like we saw, and then hitting that point. So theta is really those two things. Both of these work. They're actually going to get us to this same spot on this circle. So, as we saw, there are really two answers here. If you decided to write 370.3 degrees, it's the same exact answer. So this pattern is still holding up. So try to write this in words on your own for number 4, the relationship that we recognize between two complex numbers in polar form and their product. I'm going to spell it out. When multiplying two complex numbers, in polar form, first what we'll do is we'll multiply the radial distances. And second, what we'll do is we'll add the angular distances. And that's our quick process for multiplying two complex numbers in polar form. So we have two complex numbers. Let's call them z times u, where I'll actually write them out. We'll call one z and say that's equal to r, I'll call it 1 cosine theta 1 plus I sine theta 1. Doing this because we have two different angles, because we're going to have two complex numbers. And let's call the other u equals r2 cosine theta 2. Actually, I'll call this one not u, but z. We'll go z1 and z2. That might make a little more sense right now. Cosine theta 2 plus I sine theta 2. Well, our product of these, if we multiply z1 by z2, we get, we'll multiply the radial measures, r1 and r2, times cosine of what we're going to do is add the angular measures, theta 1 plus theta 2 plus I sine theta 1 plus theta 2. And that's how we can write the product of two complex numbers written in polar form. All right, last task here. This is optional. If you don't care, if you're unconcerned with this, we pretty much just came up with this relationship here. However, this wasn't technically a proof of it. This is just two examples. And technically, looking at two examples doesn't prove it for everything. So if you want to see the actual proof here, it's pretty cool. Brings back some stuff we've learned about. So if you're done, have a nice day. You don't have to watch the rest of the video. If you're interested, this is the proof of why it's true. All right, so we have two arbitrary complex numbers, z1, z2, using a, b, c, and d as our real number coefficients here. We want to write the product in polar form. Well, z1, I'll call some arbitrary point, let's say right here. This is z1. z2 is a different arbitrary point. It's maybe, let's say, up here. All right, and we have some angle measures too. To get to z1, this we'll call that theta 1. And to get to z2, that's theta 2. And both of them have their own radial measures. This is r1, and this is r2. We'd draw right triangles out of those and would end up getting our polar form of these, but we actually kind of know our polar form. z1 in polar form, I'll do that red. Stay consistent. z1 would be r1 cosine theta 1 plus I sine theta 1. I'm not going to include the parentheses right now on the thetas. And z2 is r2 cosine theta 2 plus I sine theta 2. We'll keep those in mind for a second, but really all we're doing is multiplying these. I'm going to start off by just multiplying them in this form, and then we'll substitute some things back in. z1 times z2 is equal to, well, z1 was a plus bi, and z2 is c plus di. Multiply those together. If you want to use a table to organize your thoughts, you can. A bi, c di. We get a times c, bci, ADI, and BDI squared. So AC plus ADI plus BCI plus BDI squared. couple things here. I know that I squared is -1, so I have AC plus ADI plus BCI minus BD. Let's reorganize some things real quick. So AC and BD are like terms, they don't have an I, so let's group those together. AC minus BD. Also, these are like terms, and I notice that they both have an I in them. Let's factor that I out. So we'll have plus I times the quantity of AD plus BC. Not so bad. All right, let's just plug in all the things that we know here. What is this length A? Well, let's look back. If we're to go into our triangle here, the length A was here for Z1 because that was A plus EI. That's this horizontal length, A. This length was B. So A here is really just R1 cosine theta 1, kind of like we saw in the first example today. B would be R1 sine theta 1. Similar arguments up here. This is C, this is D. C would be R2 cosine theta 2, and D would be R2 sine theta 2. Well, let's just substitute all of those in for A, C, B, and D. So in place of A, we know that it's R1 cosine, I don't know, I call that a theta, cosine theta 1. And C is R2 cosine theta 2. I'm going to run out of room, so I'm going to slide this over this way. Minus BD, well, B is R1 sine theta 1. And D is R2 sine theta 2. Plus I times AD plus BC. Well, A times D should be R1 cosine theta 1. D is R2 sine theta 2. Plus B was R2 sine, or sorry, R1 sine theta 1. And C is R2 cosine theta 2. All right, let's do some quick factoring of some stuff out. I noticed that both of these have an R1 and an R2, both terms here. So let's factor out R1, R2. And I noticed not just there, but it exists for everything. We have R1, R2. So technically we can factor that out of everything, just to save us some time. So factoring that out of everything, we have R1, R2 times cosine theta 1, cosine theta 2, minus sine theta 1, sine theta 2, plus I cosine theta 1, sine theta 2, plus sine theta 1, cosine theta 2. And we'll close this big bracket here. All right, so now that we have this rewinds us to something we learned about previously. This right here, cosine theta 1, cosine theta 2 minus sine theta 1, sine theta 2. This is the addition identity. Or sorry, not addition, subtraction identity. So we're subtracting. Wait, yeah, it is the addition identity. I'm sorry. It's the addition identity for cosine. Therefore, we can replace that whole thing there with this cosine theta 1 plus theta 2. This expression right here, this is the addition identity for sine. Sine theta 1 plus theta 2. So now we can just replace those two expressions with the more simple addition identity expression. And our final answer becomes that when we multiply z1 by z2, we get r1, r2 multiplied together cosine of theta 1 plus theta 2 plus I sine theta 1 plus theta 2. And that's that relationship that we just noticed on the other side. We have now proven it for any complex number because we chose two arbitrary ones that could be anything. All right, hopefully this lesson helps. If you have questions, please feel free to contact me, attend office hours, or come in for tutoring. You'll have an assignment for this as well. Hopefully it all makes sense. Please let me know otherwise. Have a good day.